Okay, here we go. Are we good? Yes. So there we go. Yeah, the GIF. Cool. And remember, by the way, like this design is on the GitHub page. You can download it and play with it yourself. By all means, like you're encouraged to do so. We did play with it ourselves as well in class last time. We were manipulating the control signals. But the big takeaway here is, okay, yeah, we've got data input in the clock, right? Like, yeah, we're toggling those things. But like once we've put the data in like the A and the B register, we were able to like do the addition and store it back in A just by manipulating the control signals. And all the control signals are doing are telling like one component to input and another component to output and variations of that, right? By activating and deactivating inputs and outputs of the different like modules in the system, we're moving data around and number crunching, which is pretty cool. And then, yes, we ended on this warning. I'm remembering now. We ended on this warning about if I'm doing like 15 minus 5, for example, the ALU right here is going to be, let's ignore the signals for a second. Let's go up to here. Oh, and by the way, this was also what I was saying. Like this is the program to do that arithmetic. Where here I'm adding, I guess I'm adding 15 and 4, okay? So let's say here, we're right here, okay? Let's say I have 15 in here, 4 in here. And remember, A is always outputting 15. It's just this, okay, the signal breaks, but because this is always outputting 15, but the driver here controls whether or not this actually gets to the bus. But there's always a 15 on that queue in this example. Similarly here, there's a 4 there at that queue being output, but it's blocked by the driver, which is what we want because we're controlling access to the bus. Very important. But you'll notice that, again, it branches, and the branches are always going into the adder. And the adder is a non-sequential circuit, meaning it doesn't require like clock cycles to do its thing. You input, you output. Because remember, it was just a series of basic logic gates, ANDs, ORs, XORs, and right, to do the addition. So whatever inputs are here, it automatically, without a clock cycle, the output right here is going to be F plus 4, which is 15 plus 19, right? So there's always a 19 here in this example, right? No, it doesn't. I don't need to wait for a clock cycle. There's always a 19, but we're not outputting anything to the bus. In the same way here, right? Until this is activated, nothing gets output to the bus. I realize here we could see that it is but that's just the picture. There, now we don't need to be worried about what data is on there, right? So there's a 15 here, and it's always being fed into here. 4 here, always being fed into here. There's a 19 right here, but we're controlling whether or not something is being output here. So right now, 15, 4, 19. If I were to output the adder to the bus and put it into A, okay? Immediately, if A becomes 19, Q is 19, meaning 19 is put back into here. Right? So you might be worried, like, well, wait a minute. It's always taking, like, okay, this was outputting 19, but if we have 19 plus 4, that's going to be 22. So immediately after a clock cycle, this is outputting 19. There's still a 14 here. That turns into 19. Immediately, this turns into 22 because 19, which we put into A, plus 4 is 22, right? So this is outputting 22 on the data bus. And you might be thinking like, well, hold on, the addition should have been 19. It was, because the 19 was safely stored in the A register. And if you're like, well, is it possible that like, okay, well, we stored that to the A register, but on the clock pulse, what if the 19 went to here and that got stored into the A register? No, because of the flip-flop. It'll only ever store on that clock pulse. The instant that clock changes, that's when the register stores. It's not like when the clock is high, it can store whatever value is on the bus. No, it's that instant. That's the whole point of the flip-flop. So yes, this will be outputting 22, but as soon, like realistically, if I was doing addition, I would stop outputting from the adder, and A would be still storing 19, and B would still have 4. Was that clear? Happy, sad, yes, no? Are you happy? Why didn't you say something before? You made me look like a fool. Gee, 19 plus 4 is in fact 23, everybody. You're right. Gee, if you were sitting there going like, what am I missing? How is it 22? No, you were right. I was wrong. I'm sorry, everybody. I can usually do arithmetic on my own. Good catch. Good catch. Geesh. Now it's going to be on YouTube. Oh, man, everyone's going to make fun of me. I think we'll be okay. Good question. Okay, any other questions or anything about that? That was just a warning. Be aware of what's stored where, when it is, and the intentionality of what we're doing, right? Like, oh, suddenly it's 23, not 22. Suddenly it's 23. Well, yeah, but that's just because we just happened to store the result back into A. That's all. All right, next topic. Cool. Address, register, and RAM. Well, look, we already know that what like the RAM is going to look like. We already built RAM, right? But we never incorporated our RAM into our system yet. And in general, we know that RAM, we've already talked about RAM. RAM stores instructions and data for the computer, although instructions really are just data, but that's the whole thing. The values in RAM are also temporary. RAM, in general, is not designed for long-term storage. In your typical computer that you're using, you have other devices on your computers designed for long-term storage. So RAM is not designed for long-term storage. It's designed to hold whatever like the computer's currently doing. Our system is going to be using RAM only. And although RAM was discussed earlier, yeah, it wasn't ever incorporated into this system. So we're going to need to make a RAM module for our system. We already know what RAM looks like. We're not going to go rebuild RAM. We're going to use that RAM component that we already looked at in digital. So as previously discussed, memory stores data where we can index the, like, we think of it like this, right? Here is a 16 bit, or no, sorry, a 4-bit RAM. So that means there's a total of 16 individual memory addresses, RAM addresses. Our design is going to be each row in this like table. We're going to think of RAM as like a table where each row is, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? Each row can store 1 byte. Okay? Make sense? So we have 4 bits for a memory address, but each address can specify 1 whole byte. The number of bits that we can use to address and the number of bits stored in that address do not need to be the same at all. It's common for all of the systems that we use today to be byte addressable, meaning you can, if you want, index individual values at the resolution of an individual byte, 8 bits. You might say, well, why not address individual bits? Well, that's crazy, right? A byte is a nice good chunk, and there's historical reasons for why 8 bits, but it's outside the scope of this course. All right, the number of unique memory addresses is called the address space. Each location stores some amount of data. That amount is called like the addressability, byte addressable. The amount of data in a memory location is independent from the number of memory addresses. Most computers are byte addressable, like I just said, meaning, yeah. This is not a requirement, however. You do not need to have a byte addressable computer. You can have a bit addressable if you want it. That's just, again, like I said, that's just crazy. The total amount of data storable is the size of the address space times the addressability. So if I have 16 memory addresses, and each address can store 1 byte, that's very simple multiplication. Ugh. How much data can I store? Well, okay, stop talking bits. Bits, you're crazy. How many bytes? If I have 16 addresses, each address can store 1 byte, but I have 16 of them, how many bytes?
16 bytes.
Yay, very good. Yes, very simple. Now, of course, if you wanted to know how many bits, okay, well, what's 16 times 8?
128.
There you go. I'll assume you're correct, but my ability to do arithmetic today is, who knows. All right. Any questions? Okay. In the above example, a total of 16 unique memory addresses exist. Each is represented as a row. The memory address is included on the left. And here I'm showing like A, B, C, D, E, F, G. The fact that it's an A, it's a B, it's entirely irrelevant. It's just each character is just some data. That is 1 byte. Each address is represented as a row, each memory location, yeah. So this means, in this example, there is an address space of 16, locations 0000 through 1111. If you like binary, or if you like hex, we would say 0 through F. Cool? Happy? Sad? Awesome. All right, with an address space of 16, a total of 4 bits would be required to index each individual thing. The data stored in each 16 addresses were 16 letters, like I just said. Okay, whatever, we've covered this. In the current ESAP system being built, the address bus and the data bus are going to be shared. If we go back, let me go back real quick here. If I go back to here. No, maybe it was here. The bus, yeah. Remember here, so we had, this is like what I called like the address bus, and this was the data bus, okay? They were, as far as we could tell based on this design, they were entirely separate. Okay, fine. Oh, and we've got like the control bus, which is just, it's the control logic signal lines. So they were entirely separate, but in our design, we're actually going to have a shared address bus and data bus. But the data bus is 8 bits, but the address is only going to need 4 of those 8 bits because we need 4 bits for the 16 memory address locations. Cool? Cool. All right. Okay. The reason for this is due to, okay. However, even though the data bus has a total of 8 bits, only 4 bits will be used to index memory. Now, in general, when I teach courses, I like to go for a much more like discovery-based strategy where we kind of like discover why things go the way they go as we go. For this class, at least for like this first iteration of the class, I've had to take a little bit more of a like dictatorial approach where it's like, this is the way it's going to be because this is the way it's going to be, and let's work towards it. So, you know, bear with me on that. But the design we are working towards, yes, there's an 8-bit address or memory data bus. That means all the data that can be moved around on the bus can be 8 bits wide. Okay? But only 4 of those bits will be used to address memory. With 4 bits, we can only have 16 memory addresses. So you might be thinking, well, if we just did the 8 bits, we can have 2 to the 8, 256 memory addresses, which is way better than 16. 16 is rather small, right? But 256, well, look, still small, but a heck of a lot better than 16. You're right. However, due to the design that we're working towards, the architecture of the either simple as possible design, we're only going to use 4 bits. And this is going to be due to some of like the architecture's physical limitations and how we're going to design instructions, which we're going to see in a week or 2 or something, right? But there's method to the madness, but right now it's a bit of a mystery, and I know, I'm sorry. Any questions about that comment? Okay. So, the reason for this is due to how program instructions will be encoded. 4 bits are for the instruction and 4 for the operand. Basically, remember, we have 8 bits. If I have data, remember, and also RAM stores data and instructions. Now I could have data that is 8 bits, that is like 1, 1, 1, 1, 1, 1, 1, 1. Oh, well, that's 255, right? That's the data 255. But if we are encoding like an instruction, usually our instructions has like an operator and an operand, basically like a function call with an argument, right? So if I were to say like add, maybe add's bit pattern is like 1010. Don't ask me why it would be 1010. It doesn't matter right now. But this means add. And what do I want to add? I want to add the number 1. Right? So that's why, based on that. Or maybe I want to say like load into register A. Maybe load is 0011. Again, I made that up right now. That doesn't necessarily mean load. What do I want to load? I want to load memory address 1111 into register A, right? So only 4 bits can be used to index RAM, because 4 bits are used for the instructions, like the operand, the operator, and 4 for the operand. If I have 4 bits for instructions, how many possible instructions could I have? Come on, you better know this. Let's go. Come on. 16. And if you're like, how did you know that? You're in trouble. I can't help you anymore. Now, to be clear, we are here. We don't start talking about instructions until here, which might be a week or 2 away, right? So let's not worry too much now. I just kind of jumped ahead to give you a sneak peek to justify why 4 bits for RAM. This is purely a design decision. We could redesign it entirely differently to get a different thing and still achieve the same like computation, but in a different design. But we're keeping this relatively simple. Simple doesn't mean trivial, and it doesn't mean not interesting. It just means not complicated, right? So that's what we want. Okay, so details on how instructions are encoded will be talked later. So with 4 bits, a total of 16 unique memory locations can be indexed. The system will store 1 byte in each memory address, like most systems. A total of 8 bits will be stored in each. Yeah. This means the system can store up to 16 bytes of data in RAM. So, interestingly, so many of you in here are too young to remember this amazing thing that happened at one point in time. So until the late 2000s, early 2010s, a typical computer was 32-bit. It had a 32-bit address space. Okay? Raise your hand if you're old enough to remember those good old days. I do. One other person. Yeah, there we go. Cool. So 2 to the 32. Okay? That means, what is 2 to the power of 32? Someone type that in real quick to their Google. Oh, 4 billion something, 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 something. Okay, cool. So that means, now you could get clever with your engineering, but that means effectively that you could only, your computer, based on the physical design of how RAM was, if it only had 32 bits to index RAM, you could only have that many unique memory addresses. And if it's byte addressable, that's how many bytes we got. Now, you might say, okay, 4 billion, that's a lot. That's 4 gigs. Okay? I remember getting my first computer, like the first computer I bought, and it had 2 gigs. And I remember my dad being like, well, the one that you bought by default came with like 1 gig. My dad was like, get 2. Right? I was like, oh, baby, this is going to be wild, right? Like 2 gigs. Wow, right? I mean, this was, and that was in like 2006, I think I bought that in my first computer. So anyways, the good old days. Now, how many gigabytes of RAM do you have today in your computers?
I have 16.
You have 16? It's pathetic. Who can beat 16?
I have 64 on my PC.
Well, there. Okay, see, that's what we're talking. Now we're talking, yeah. Can anyone beat 64? No? All right, well, way to show off. Well done. That's a lot, right? Well, of course, 4 is a lot less than 64, but the old design, just it couldn't index those things, right? So That's why there was the shift to like 64-bit, which actually created some issues with like the CPU architecture and the instruction set, yada, yada, yada. There was a bit of a to-do at the time. But it was pretty exciting because like, well, now that limitation was gone, right? It's pretty cool. So with 64 bits, you could get a lot more memory addresses, which is fantastic. Cool. A neat little history lesson there. Does anyone else remember that glorious time? Do you ever remember seeing like System 32 on your computer and like program files 32, 64? What's up with that? It was based on how the programs were. Yeah. I don't know if you really see that anymore these days. Everything's probably migrated to 64. But a couple years back, Mac just said, screw it. If it's not 64-bit, it ain't running on this anymore. I'm pretty sure like they just cut it off, where Windows was still a little bit more forgiving. But anyways, cool. Address register. So, okay. Any questions about that little history lesson? I thought it was cool. So, having memory addresses and data share a bus poses a problem for the system. Because the values on the bus are transient. They are designed to be transient. The value I have on the bus is only supposed to be there temporarily, right? So imagine, here's my goal. I've got data in RAM, okay? I want to output the value stored in memory address 2 from RAM, okay? We have a shared address and data bus. So if I've got a bus, and I need to go to my RAM module, RAM, right? I need to input into this address 2, okay? But then I need to output whatever's in address 2. But there's a value on that bus. So like, I can't be like, okay, get this, and then immediately turn it off, and then RAM's going to be like, well, what address? Like, we need to be able to tell RAM what address from the bus, and then put information onto the bus. But there's information on the bus, which is that memory address that I need. And what happens if we try to put 2 pieces of information on the bus at the same time? It ain't going to work. We're going to create a short circuit, and we're going to be very unhappy. So we got a bit of a problem. But fortunately, there is a hilariously simple solution to this problem: a register. Well, what we can do is take the data from the bus, put it into a register, and then output the data onto the bus. It requires an additional step because we know every time you want to store something in a register, you need a clock pulse. So it's a sequential thing, so it needs to be synchronized in some way. But, I mean, this solves the problem of having a collision on the bus. So the values on the bus are always changing, but the index memory location may need to be static for some time, right? So like something like this. Now, again, this is saying this is 8 bits. This is a splitter to take 0 to 7 bits. Here's the 0 through 4, so the least significant 4 and the most significant 4. The most significant 4 are completely ignored for that address. So if I were to try to put information onto here and then output information, like, it ain't going to work. If I were to run this and try to do it, it's going to crash. So not particularly useful configuration of RAM component of a RAM, that should be a lowercase a, with a shared address and data bus. So yeah, mind the splitter. Okay, remember only 4 bits. Yeah, okay. It's possible, for example, to store the value 4 in memory. So okay, like here's the problem I'm saying. Like imagine I want to store the value 4 in address 2. Okay, so tell RAM to go to address 2. Okay, and you look at this and be like, well, that's easy. Turn this toggle on. Great, it's where address, you know. And now put the data 4 in. Ugh. Well, there's all. I can't. I need 2 pieces of information to be on the bus. So the solution is add a register, just like this. Okay? Take a moment, look at this design, and make it make sense to you. Here, let's just do this. Oh, don't look, spoiler. Memory? All right. I was hoping we'd have the one where it wouldn't work. But of course, the one where it wouldn't work, hopefully it's obvious why it won't work, right? Go back and think of the example. I want to put some value in index or an address 2. Okay, so I turn that on to address 2. Now address 2 is there. I need to put data on the data line. What data do I want to put in there? Technically this could work, but with only one value. The only way I could load value into RAM, what value could be loaded into RAM, each memory location with this design? Yeah, that's just it, right? If I put 0 on the bus, we're indexing address 0. I could clock pulse and say, yeah, RAM in. But the only value that can be on the data bus is the memory address right now. I put in a 1, 1, 1. A 2, 2, 2, and so on, right? Not very useful. Okay. So we have this design where I can latch in an address, then change the data on the bus, but meanwhile, this is still always outputting the address that we just stored in the address register. So this is called an address register. How many bits can be stored in this register? 4. Why? Well, because that's the design that we just made, right? I could make it more if I wanted more in, but our design, we're going to have 4. So what do we want? Let's put an address 2, clock pulse, boom. Oh wait, I need to enable the address register. There we go. And now if we hover here, we can see, yep, the value 2 is there. That's good. Actually, no, let's put an address 3. Forget that. Let's do 3. There we go. Okay, cool. Cool, and we can keep pulsing this. There's nothing like here. Let's turn this to. Oh, there's still a 3 in there. Good. What data do we want to put in address 3? Someone yell out some data that can fit in 8 bits that I can easily know the bit pattern for. 32. What's that? This one? 1, 2, 4, 8, 16. Ah, you should be impressed. RAM in. Clock pulse. Perfect. There we go. Now, let's turn off. There. Okay, and we can RAM out. Well, we see 2x, or like hex 20. Well, that's 2 16s, 32. Okay, cool. Good. But now let's, man, this is kind of annoying. Let's go to address 0, so clock pulse. There we go. All right, RAM out. Now, what should be stored in address 0? It's going to be 0. Now, your shrug was actually interesting because really, when you turn on a computer, RAM is always kind of like whatever, right? There's no zeros there. It's just the transistors are always just kind of like arbitrarily set, right? So unless I go and intentionally set it to anything, usually you have garbage in your RAM. Now here, it does, if I right-click this, actually we can see what's in RAM, which is kind of nice. So we can see what values are there. It starts all at zeros. Now if you're looking at this being like, that's not a 0, yeah, we just changed that to 32, right? So yeah, there we go, cool. Here, let's put something in address 0. Let's see if it changes in real time. Oh no, we want RAM in. Ah, look at that, it changed, look at that. I was afraid I'd have to like close it and reopen it, like it would be static, but that's kind of neat. Cool, cool. Neat. So this solves the problem of like, this is a very common simple, straightforward solution to a problem of like, oh, we need 2 different sets of data on the data bus. Okay, just isolate one piece of data and you're good to go. Yeah? This is a very common thing that we're going to see done several times in different scenarios as we go in the course. We have specialized registers to hold on to data even if it's like temporary. The A register, okay, RAM is but like its design is that it's transient. Nothing's really supposed to be there forever. Registers are even more temporary. But you know, you put something in register A and you hold on to it for as long as you need. But things like the address register, things like these other variations, like these other registers that we will see, we're going to see an instruction register, we're going to see an output register, there's a bunch more. Those are even more transient. Those are always changing. They're really just temporary holding spots for whatever memory address we want to be looking at, that type of thing. Okay. So with this configuration, there's now a small but isolated address bus. So there is technically an address bus now. It's this, right? From the address register all the way down to RAM, which is what? The tiniest way, but it's there. Whoop. To return to the previous examples problem, now it would be really easy to load the value 4 into address 2, right? We did 32 in address 2, but whatever. So how could we include this RAM thing? We're going to call these things like modules, okay? So we have the A register, the B register, the ALU module. This right here we'll call like the address RAM module. Yeah, the address register and RAM are separate components, but we're going to talk about them as their own kind of like unit because they're so overwhelmingly interconnected. So here's how we can design it into the system. Boom, there we go. I put it over here. If you're like, well, hold on, you had it on the right-hand side. It doesn't matter where we put it, really. I'd liked it over here more. So there, we've got the address and RAM. Just to make sure everything's there, 8 bits to here, but we split, so only the bottom 4 bits goes to the data. Clock is connected to the clock, which is also connected to the RAM's clock. We've got some control signals here for storing data in RAM, so RAM in, RAM out, and the data line. It's bidirectional, meaning if we're storing data, whatever data is on this gets stored into RAM. If we're outputting data, whatever data is in here gets put out to there. We're using the bidirectional version. We could have used the two data ports, but we're using the 1 data port. Then I put all the control signals down here just to have them in a nice spot there. So these were the control signals we had before. A, B, ALU if we're doing subtraction. But now we have RAM out, RAM in, and address register. Okay? Cool. And we can still have our little output lines here to see whatever's on the bus. That's the idea. There's our design. Pretty cool, right? So notice that the RAM module was added to the left side. This is a design style decision. It's not important where it's placed. The motivation for putting it here is it corresponds exactly with how this is like the simple as possible design architecture. And it had it over here, so I put it over there, right? Below the clock, because the clock's right there. Cool. So it's just to follow that. I actually spent a lot of time thinking about how we were going to lay it out. Originally, I thought what I could do is have originally, what I was going to do was have everything on this side. But the problem with that is the computer grew way too long. And I couldn't generate pictures. It wouldn't fit on the screen well, right? Our screens are widescreen, not, So it really didn't fit well, unfortunately. What I liked about doing it all on one side, though, is I could have the data bus all on one side. And what was neat was all the control signals were also on the other side. Where here I have to kind of split the control signals to both sides. Not a big deal, but it is what it is. Just to give you an idea of why it's being designed this way. So now, imagine I want to do some arithmetic, okay? but we're going to make use of RAM. The example we're going to use is going to be a little, I mean, it's a little contrived because I'm going to input data into RAM and then retrieve data from RAM and put it into the registers to do addition. You might say, just go directly from input to the registers. Yeah, but that's not as fun, right? We added a new RAM component. Let's use the new RAM component. So let's say I want to do 15 plus 4 minus 7, okay? So for demonstration purposes, the high-level program to be executed on the system will be this idea. Load the data into RAM. So we want to load 15, 4, and 7 into RAM. Then calculate the sum of 15 and 4 and save the result to RAM. Then calculate the difference between the calculated sum and 7 and save the result to RAM. That's what we want to do. Okay? Now, think about what that means, right? I need to store data, so I'm going to input data here, and I want to store it into RAM, but I need to specify the addresses, which we're going to specify with this too. Then I want to address RAM to put the data from RAM into A, data from RAM into B, calculate the sum and output it into RAM, but we need to specify the RAM address. Then from RAM, put the sum into A, put 7 into B from RAM, calculate the difference, and store it into RAM. It sounds like a lot of steps, but the steps are so straightforward. Just move data from here to there, there to there, there to there, there. We're just moving data around. It's just swapping data while being very careful of what our control signals are set to. Any last questions before we wrap up for the day? All right, I'll see y'all later.